Now we turn to the final part of today's session where we have a little bit more information on Fourier transforms, which is mainly thinking about differentials. So the really nice thing about Fourier transforms is that if you have the Fourier transform of a function f, so that's in the first line, g of k is the Fourier transform of the function little f of x, and it's very easy to show that the Fourier transform of the differential df by dx is just ik times g of k. You can imagine how this could be useful if you've got a function and you want to evaluate its first or second derivative, then you can do that using Fourier transforms rather than, for instance, finite differences. One classic example, something that I use a lot in my research, is solving the Poisson's equation in periodic boundary conditions. So you can see that in the third line there. Del squared phi, so remember del squared is shorthand here for d2 by dx squared plus d2 by dy squared plus d2 by dz squared, is given by minus rho, the charge density, divided by epsilon naught. Remember that rho, the charge density, is a function of space, so that'll vary from point to point, and typically that'll be specified on a grid. So then if you Fourier transform that equation, you can show that minus k squared times the Fourier transform of phi is just equal to minus the Fourier transform of rho divided by epsilon naught. So to find phi, we simply take the Fourier transform of rho over epsilon naught, divide by k squared, and perform an inverse Fourier transform. And this simplifies the solution of the Poisson equation, so long as you can work in periodic boundaries. You have to be, of course, careful where k squared is equal to naught, because that would involve dividing by 0. Fortunately, you can show quite simply that the Fourier transform at that point is equal to the integral of the charge density over your domain. Now, if you have a periodic charge density, which is not charge neutral, then you're going to have an infinite energy, which is generally considered to be a bad thing. So typically what people will do when they're using this kind of technique is either have a charge neutral system, or else if they have a non-charge neutral system, they will just set that k equals 0 value of the Fourier transform of rho to 0 to reflect the fact that it should be not have an infinite energy. You have to think a little bit carefully when you're trying to deal with charge densities that aren't periodic. So you can do that just by adding empty space around whatever charge density you have. Now in my research, where we're trying to look at systems of atoms and molecules and solids, if you have a molecule and you want to solve solve the Poisson equation for its potential in a periodic fashion, typically what we'll do is we'll put it at the center of a box with lots of vacuum around it. You then check to see how much vacuum you need, and you can see that the potential will converge. It's an approximation, but it's something that you'll be playing with in the sort of the more advanced parts of the tasks. Something you need to be aware of is that the potential can be long-ranged. Of course, for a single charge it goes as 1 over r, and therefore it can be a little bit slow to converge. You just have to watch out for that. You also, of course, have to watch out for boundary conditions. Some technical points to cover here at the end, the most important of which is to talk about a phenomenon called aliasing. So if you've got a time series, in other words a function of time, that you're sampling at a particular rate where the spacing between samples is delta, so delta is a time, then there is a frequency which is known as the Nyquist or the critical frequency, 1 over 2 delta. If your time series has frequencies that are above that in it, then you will find that you will get what is called aliasing. So you'll find traces of those very high frequencies appearing to contaminate your Fourier transform. So you have to be very careful in terms of the rate at which you are sampling a function. This, of course, should be fairly obvious. If you've got something which is oscillating very rapidly, and you are sampling it at a rather low rate, then we're going to have the same kind of situation we saw in the first video, where you've got the problem with interpolation. You're going to have ringing between data points. So if you have a rapidly oscillating signal, you need to sample it rather frequently. There are other transforms which are available. There's a set of transforms called Wavelet Transforms, which are in use in certain areas, often in image processing. The maths is a little bit more complex, but they have certain rather useful features. In particular, wavelets themselves are optimally localized in both real and transform space, Fourier transform space. So they can be very good in terms of representing your data in a compact way in both real and reciprocal space, real and Fourier space. Mathematically, people use Laplace transforms. Those aren't really used much computationally. And if you're working in circular or spherical symmetry, then you can use a Hankel or a Bessel transform, which allows you to do one-dimensional transforms for the radial term and then work exactly with the kind of angular terms that you would get. This kind of thing is often encountered in, for instance, atomic calculations where you will have spherical symmetry. So I would encourage you to go and do the final set of questions. You'll see from the notes that this time I haven't actually split it into in-class and further work. I would say that if you want to just check that you understand what you're doing, then you should probably just do the first 4 or 5 questions up to the point where you calculate the potential using a Fourier transform on a grid. The last few parts are a little bit more challenging. They're worth trying. There's quite a lot of fun that you can have there. They're nice, powerful calculations, but they will be published along with the in-class work on Tuesday. Do, if you have time, have a go at the assignment. There you're looking at using Fourier transforms to detect edges. So we use a set of spins from the previous session, and of course you've got these big domains of positive and negative spins, and you have an edge between them. You can play around with first and second derivatives there and look at whether you can find edges.